Well, hi, I'm Herb Gross, and welcome to Gateways to Algebra, where today we're going to begin what I hope is a delightful and awesome journey into the world of logic and critical thinking. Now, some of you have already decided to embark on a career that involves math and science and other quantitative subjects, and so you know why you're taking this course. Others are probably saying, why me? At least I know that's the way I was when I was in college. I was a math science major, and I had to take courses in Greek literature, Western civilization, psychology, anthropology, and I said, why me? All I want is math and science. And the truth of the matter was, it took me a long time to realize that to solve the problems that are so complex in the world that we face today, it takes a knowledge of all disciplines of human endeavor. In a certain sense, it's the literature and the humanities courses that teach us the values that underlie our civilization. And it's the behavioral and social sciences that teach us where we came from and how we got here. And it's the mathematical sciences and logical thought that teaches us how we predict and plan the future based solely on our knowledge of the present and the past. And putting all of these things together is what education is all about. We must never choose between human values and subject matter content, but rather what we're going to discover is that if we teach the two of them side by side, each emerges more powerfully than if it's been taught to the exclusion of the other. Now, one of the things I want to begin with today is exactly what it is that algebra deals with and what makes it different from all other mathematical subjects. So I thought I would start with a very simple quiz. On the card that I'm going to show you now are 4 words, and you're supposed to tell me which of these words is inappropriate in the given grouping. Okay, here we go. Arithmetic, geometry, trigonometry, algebra. And in case you didn't already catch on, let me give you a little clue. You see what's interesting here? The top 3 words all have the MET stem. And that's the Greek word that means measure. To measure. See, G is the Greek word for earth. Trigon is the Greek word for triangle. So geometry is the measure of the earth. Trigonometry is measure of a triangle. And by the way, there are other Greek suffixes that you might be interested in knowing about. For example, logos is story. So when you say geology, it's the story of the earth. When you say psychology, it's the study of psychology. But look at the word algebra. It doesn't seem to belong in the above grouping. And in fact, it's believed that the word algebra is derived from the person named Al-Khwarizmi, who was an Arab who lived prior to the Middle Ages when the subject algebra was invented. The word algorithm has the same stem as the word algebra. They come from the same word. You see, what algebra deals with is the systematic study of arithmetic. What algebra deals with is how can you use the principles of arithmetic to predict answers without having to resort to trial and error and other tedious techniques. See, an algorithm, to put it in simplest terms, is a recipe. You see, let me give you an example of an algorithm. Let me show you how you can solve a problem that you've never seen before simply by remembering that it fits the same recipe as something that you have seen before. Let me just show you sort of a simple thing over here. I'm going to give you look at this particular addition problem. You don't have to do it, I just want you to look at it. 381,947 plus 264,093 plus 593,876. Is there anybody amongst you who believes that you can't solve this problem? Is there anybody who finds this a problem that can't be solved? Oh, I don't care whether you want to say it's tedious or it's messy or there's a lot of digits here. Is there anything difficult about solving this problem? The reason I bring this up is these are all 6-digit numbers. The likelihood that you've ever written down this number before is 1 in a million. The likelihood that you've written down this number is 1 in a million. and the likelihood that you've ever seen this number is 1 in a million. In other words, if you've ever added exactly these same 3 numbers together, it's like hitting the state lottery 3 consecutive times. You see, the chances are more than trillions to 1 against the fact that you've ever done this problem before. But why is it that you don't panic when you see this problem? It's because you know that the recipe for place value addition always remains the same. You know you're going to say 6 plus 3 is 9, plus 7 is 16, put down the 6 and carry the 1, etc., etc., etc. So that even though you've never seen this problem before, there is a systematic approach to solving this problem. A companion of that, see, systematic approach is just one aspect of the overall problem. A companion to that is what we call logical thought. Logic is the art form, so to speak, by which we try to solve problems that would be very, very tedious by trial and error and reduce them to a format that gives us the answer relatively quickly. For example, suppose I'm trying to unlock a door, and I have just 2 keys, and I know that one of those 2 keys will unlock the door and the other one won't. Now, my object is to unlock that door as fast as possible, and it takes me about 5 seconds to test the key. What is the best way for me to get the door unlocked? Should I sit down and think of a real logical approach, or should I just take one of the keys at random, put it into the lock? If it opens the door, I've solved the problem. If it doesn't open the door, I know the other key has to work. So if I can test the key in 5 seconds without any logic and just trial and error, I can get that door open in less than 10 seconds. But now suppose instead I have 1,000,000 keys, and I can test them even at the rate of 1 per second. And by the way, for those of you who aren't aware of this, 1,000,000 seconds is just about 12 days. And by the way, if I had 1,000,000,000 keys and had to do this, 1,000,000,000 seconds is around 31 years. Believe it or not, 1,000,000 is to 1,000,000,000 as 12 days is to 31 years. But the point I'm making is if I had 1,000,000,000 keys or 1,000,000 keys and I could test 1 key per second, it's going to be very, very tedious to find out which key opens the door. And at that point, it may be advantageous to look for a logical pattern. Now, let me show you in sort of a riddle form how logic works. I don't know if you can see my writing here. Let me just try to emphasize this a little bit more. Make it nice and dark over here. What I have over here is an abbreviated checkerboard. A typical checkerboard is 8 by 8. This is a 6 by 6 checkerboard. I have 12 checkers. So I have 12 checkers. Now what I'm going to do is I'm going to put a checker in each of these 4 corners. By the way, this is not a particularly deep problem, but I made it up myself, so I'm very proud of it. The object now is to take the remaining 8 checkers. See, I've put 4 in the corners. There are 12 checkers altogether. The object is to take the remaining 8 checkers and put them down on the board in such a way that no row, column, or diagonal has more than 2 checkers on it. You understand the problem? No more than 2 checkers on any, not just in the rows and the columns, but on all the diagonals as well. Now, one way to solve this is by trial and error. Another way is to use logic. Is to look at this problem and say, wait a second, what do we know about this problem? Let's at least see where we know the checkers can't go. Since there can't be any more than 2 checkers to a row, the top row already has 2 checkers, so let's cross out all the remaining squares on the top, because we can't put a checker there, because any checker on this row will give us more than 2. In a similar way, we can't put any more in the first column, because there's already 2 checkers there. And we can't put any more in the bottom row, because there's already 2 checkers there. And we can't put any more in the top, in the last row, because there's already 2 checkers there. Also, we can't put down any checkers on either of these 2 diagonals, because there's already 2 checkers here. Now we've figured out where they can't go. How many squares are left? 1, 2, 3, 4, 5, 6, 7, 8. How many checkers are left? 8. What does that tell me? It tells me that either putting the checkers here will work, in which case this is the only possible answer, or putting the checkers here won't work, in which case there are no answers. In other words, do you notice what we did over here? We were able to solve a problem without doing anything else but using our logical minds to show where the checkers couldn't go. Now that's what logic is all about. And the question is, how does this apply to algebra? Remember, algebra comes after arithmetic. And consequently, any subject that you study should always begin with its first chapter being the last chapter of the subject that you learned before. So you see a continuity this way. What is the difference between arithmetic and algebra? Where does arithmetic end and algebra begin? And the amazing thing is, if we do this properly, we discover that arithmetic never ends. Or equivalently, algebra never begins. You see, one of the definitions of mathematics is that mathematics studies the quantitative relationship between things. Now, quantitative relationship means, given one quantity, mathematics gives us an algorithm, a recipe that tells you how you compute another item. Those things are called formulas. And the amazing thing is that formulas are neither arithmetic nor algebra, but they give you the bridge that shows you how one is related to the other. Now, because many of you may be frightened of a new subject, in other words, some of you may be afraid of the word algebra, let me begin with something that I hope is much more non-threatening. Let me see if I can do something over here. Let's suppose I'm a teacher of geography, and I want to see if you know that Sacramento is the capital of California. Now, one way of finding this out is to give you a fill-in-the-blank problem. I can say blank is the capital of what? Blank is the capital of California. I could also have worded it as Sacramento is the capital of blank. Both of these sentences, when filled in properly, will say what? Sacramento is the capital of California. But notice that psychologically, one of these two problems is easier than the other. Namely, in fact, this isn't even really called a sentence. Technically speaking, these are called open sentences because part of the sentence is missing. When we say fill in the blank, what we mean is replace the blank by the word or words that turns the open sentence into a true statement. For example, what this means is, what word has to go into the blank to make this a true statement? Well, the only noun I see here, proper noun, is California. Now, the problem is, when I see California, it's not clear to me that I'm going to think of Sacramento. I might think of Los Angeles, I might think of San Diego, I might think of San Francisco, I might think of Oakland. On the other hand, look at the second form, where it says Sacramento is the capital of blank. Here's the interesting thing now. The only noun I see over here is Sacramento. Now, I might not know that Sacramento is the capital of anything, but there's an excellent chance that I remember that Sacramento was in California. So I make an argument similar to this. I say, gee, I didn't know that Sacramento was the capital of anything. But seeing as it's in California, I think it's a pretty good bet I can put California in here. So even though both of these sentences, when filled in, or open sentences, when filled in correctly, will give you the true statement that Sacramento is the capital of California, the second one has a much higher success rate than the first one if students are looking for a good score. And in fact, to make this even more important, notice that the important thing here is the relationship called is the capital of. In other words, we might not be just interested in California. We might be interested in Massachusetts, Vermont, North Carolina, Florida, and notice that we can put any state we want in over here, but depending on what state we put in over here, that locks us into what the name of the city has to be. And we're going to come back to things like this in more detail as the course goes on. But do you get the idea of what an open sentence is? Now, to fill in the blank means to complete the open sentence and convert it into a true statement. Sometimes it's impossible to do that. Other times, there's more than one way to do that. Let me see if I have this written down over here for you in advance. Let's take a look over here. Let's suppose I gave you this open sentence. It says, Pittsburgh is the capital of blank. Now, the interesting thing is that it doesn't matter what you put into the blank over here. Pittsburgh is not the capital of anything. In other words, I can, by the way, be careful here. I can put the word Massachusetts in here. I say Pittsburgh is the capital of Massachusetts. Is that a meaningful statement? Of course it's meaningful. I understand what it means. And in fact, if I didn't understand what it meant, how would I know it was a false statement? See, no matter what state I put in here, this statement here is going to be false. On the other hand, look at this statement. It says blank was one of the original 13 colonies. You see, can I put New York in here? Yes. Can I put Virginia in here? Yes. Can I put Massachusetts in here? Yes. In fact, there are how many names can I put in here to make this into a true statement? Well, it says was one of the original 13 colonies. There are actually 13 possible right answers to this particular problem. See, here are no answers, here are 13 answers, so sometimes we're going to be dealing with what? One answer, more than one answer, no answers, and now the question is, how does this apply to mathematics? So let's go to something fairly simple. It requires knowing that there are 12 inches in a foot. How would you explain to somebody how you converted feet into inches? Okay, let's call it converting feet to inches. It says what? Start with the number of feet, okay, multiply by 12, and then the answer is the number of inches. Do you see why this is called a quantitative relationship? It not only tells you that feet and inches are related, but the statement 2 over here tells you exactly how you get from one to the other. So suppose we were given the problem, how many inches are there? In fact, let me go back to this previous statement over here first, just to show you something. But do you notice that this is kind of a long way to write things? In other words, I say convert feet to inches. Start with a number of feet, multiply by 12, the answer is a number of inches. Mathematicians don't like to take that long to state something. And this is how formulas come about. Start with a number of feet. Well, feet starts with the letter F, so let F stand for the number of feet. What do you do next? You multiply by 12. And what's the answer going to be? See, it's equal to the number of inches. So since inches begins with I, let capital I stand for the number of inches. Look what happens over here. If you're afraid of symbolism, this looks very scary. On the other hand, writing it out this way seems very simple. The point is that we'll call this English and we'll call this algebra, and this is the statement we get when we translate these commands in English into the language of algebra. In other words, whenever you see a letter of the alphabet, that's telling you either the number you're starting with or the number you're finishing with, and the way you're going to tell the difference is the number you start with is going to be mixed in together with other numbers. And the number you wind up with is the number that's written all by itself on one side of the equal sign. So, in other words, if I see something like this, I have to train myself the same as in any foreign language to say, oh, this means start with F, the number of feet, multiply by 12, and the answer is the number of inches. Okay? And by the way, here is one of the advantages of videotape. If at this stage you say, wait a second, that was kind of fast, he went a little bit too fast for me, hit the stop button, or hit the pause button, or hit the rewind button, and go back to the last place you were when you understood what I was talking about. Unlike a live classroom lecture where you're forced to go at the pace of the instructor, here you have the right to stop the tape and do whatever it is that you want. So I just wanted to make that point clear to show you one difference already between how we're offering the course in this medium versus how this would be as a live course. Now, coming back to what we were talking about, suppose now I have this formula. F times 12 equals I. The number of feet times 12 equals the number of inches. So somebody says to me, how many inches are there in 5 feet? Now watch how the reading comprehension comes in. 5 is modifying what now? It's modifying feet. Feet is indicated by the letter F. So in this formula, wherever I see F, I'm now going to replace it by 5. So look what happens over here. I replace the F by 5, and now the thing I'm looking for, I'm going to replace that by a blank, so we get a fill in the blank. You see, 5 times 12 equals blank. Now at this point, suppose you have a calculator. You don't understand math very well, but you have a calculator. If all you have is a calculator, and you don't even understand what multiplication means, can you solve this problem? The answer is yes. Just punch in the 5, the times sign, the 12, the equal sign, and the 60 lights right up. Now, that's one way to fill in the blank. Let's reword this problem to see something different. Now the problem is going to say, how many feet are there in 60 inches? Here's what I mean by algebra and arithmetic being parts of the same coin, two different faces of the same coin. Does the relationship between feet and inches change? No, the relationship is still what? Start with the number of feet, multiply by 12, and the answer is the number of inches. What changed over here was what part of the relationship we were given. Now we still have the number 60, but what's it modifying? Not feet, but inches. That means we have to read this problem well enough to understand that the I is going to be replaced by 60, not the F. Now we're looking for F. That becomes the blank. What does this open sentence now read? It says blank times 12 equals 60. And here's where algebra comes in. If now you have a calculator and you don't understand multiplication, can you solve this problem? And the answer is no, because the first thing you have to do is plug in the blank, and the calculator doesn't have a blank. You see, what happens over here is you see a time sign, but the problem is really solved by doing what? Starting with the 60 and dividing by the 12 to get the answer 5. You see, what's interesting is you mustn't be brainwashed into thinking that just because you see a multiplication symbol that you're going to have to multiply. The logic is that you have to recognize that since one of these numbers is missing, even though this is a time sign, you're going to solve the problem by division, okay? And that, roughly speaking, is the difference between arithmetic and algebra. You see, let me summarize this for you in words, just in case you're still nervous about the algebraic language. See, what I'm saying is, when I'm dealing with the 5 feet equals 60 inches, one way is saying what? If I start with 5 feet, it says what? Start with 5, multiply by 12, and the answer is I. See, in other words, you start with 5, multiply by 12, the answer is 60, and so there are 60 inches. Look what happens over here. This says you're starting with a number of feet, and after you multiply by 12, you have 60 inches. So now the problem is you're starting with the 60 and have to rederive what F is. And the way you say this is, look, up here, when I saw the 5, I actually multiplied it by the 12. What happened down here? Notice that the 60 is what you got after you multiplied by the 12. So now what you're saying is, if I got 60 after I multiplied by 12, obviously what I have to do, working in reverse, is to undo this step. Instead of multiplying by 12, I have to do what? Divide by 12. And all I want to point out is that the subtle difference between arithmetic and algebra is nothing more than whether you start at the top and work to the bottom, or whether you start at the bottom and work your way through to the top. In fact, see, basically, that's what happens. By the way, there is one more thing I want to show you over here. And what happens is we wind up making languages quite different in math. You see this X, this time sign? Doesn't it look like the letter X? So since we have letters of the alphabet, it could be confusing because the X could be confused with a time sign. So one of the things that we do in the language of math is whenever there's a multiplication, we don't put the multiplication symbol in, we simply put the letter next to the number. See, F12. And by the way, you don't usually say, give me apples 12. You usually say, give me 12 apples. So instead of writing F times 12, the mathematician simply writes 12F. The other thing that we do in math, for reasons which aren't really that important, is we usually put the answer all by itself on the left. So in other words, the way this formula would be written in most math books is if I stands for the number of inches and F stands for the number of feet, we would write what? I equals 12F. And what that tells you to do is what? Start with the number of feet, start with F, multiply by 12, and the answer is I. And if you're given a number of feet, that's arithmetic. If you're given I to begin with, that's then algebra, okay? So the only difference between arithmetic and algebra is whether you start with the pick a number and get to the answer, or whether you start with the answer and get to the pick a number. Now, the other thing that's interesting about mathematics is that multiplying by 12 applies to things other than converting feet to inches. For example, how many months are there in a year? 12, right? So suppose I want to convert years to months. How would I do that? This time I would start with the number of years, I would multiply by 12, and then the answer is the number of months. Notice that the step is still what? Multiply by 12. Of course, I don't want to call the number of years by the letter F. See, years starts with the letter Y, so what I might say is what? Start with the number of years, multiply by 12, and the answer is the number of months. So again, what would happen here is what? If I put 5 in here, 5 times 12 would still be 60, but now it doesn't mean that 5 feet is 60 inches. It means what? That 5 years is 60 months. Okay? See, in general, what we're saying is there are a whole bunch of times when the formula is going to be multiplied by 12. You see, in terms of a computer program, computers have what? An input, an output, and a program. The multiply by 12 program says what? Pick any input, multiply by 12, and then that's going to be the output. If we call this F, it means the input has to be feet maybe. If we call it Y, it means years. But doesn't this program work independently of what we call the input and the output? So again, what the mathematician does is generically we pick the letter X to stand for the input and the letter Y to stand for the output. Okay? And let me just show you another program this way so that you get the idea. See, the program could have been what? Multiply by 2, add 3, and then this is the output. See, in other words, to make this look more like a computer, the input is X. What's the program? Multiply by 2 and add 3, and the output is then going to be Y. So let's see how this thing works. Suppose the input was 6. And you have a calculator, and you don't understand any math at all. The first step is what? Multiply by 2. What's 6 times 2? It's 12. What's the next step? Add 3. And 12 plus 3 is 15. So if the input was 6 here, the output would be 15. That's arithmetic. See, in other words, in going from the input to the output, all you had to do to get the ultimate blank, which was the output, was to do what you saw over here. Algebra would be, suppose instead I said, hey, the output is 15, what must the input be? And all algebra says is, look, when did you get the 15? It was after you added the 3. In other words, it was what? Blank plus 3 equals 15. So to find out what the blank is, you don't add 3, but you do what? Subtract 3. See, to find out what you had before you added the 3, subtract the 3. Well, if you started with 15 and you subtract the 3, the answer is 12. When did you get the 12? After you multiplied by 2. So to see what you had before you multiplied by 2, you just divide by 2, and what answer do you wind up with? 6. You see, arithmetic is when you start with the input and go to the output. And algebra is when you start with the output and work your way back to the input. And see, that's how simple algebra really is. Now, of course, if that was a true statement, you would know that it wouldn't take 1 or 2 years to learn algebra. It would be over by this time. And that's the reason we have the rest of the course. Starting with next time, we'll look into the next layer of complication. But until that time, study hard and enjoy learning.